Hello guys, this is Paul McWhorter from TopTechBoy.com, and we're here today with lesson number 9 in our Arduino tutorial series on building a 9-axis inertial measurement system. What I'm going to need you to do today is pour yourself a nice big mug of iced coffee, and I'm going to need you to get your gear out and remember where we left off in lesson number 8. For those of you who are playing along at home or want to play along at home, I want to remind you that we are using the most excellent Adafruit BNO055 inertial measurement sensor, and we have it hooked to an Arduino Nano. If you don't have your gear yet, look in the description down below. There are links. It is important on something as complicated as this project that we are working with identical hardware. So get your gear if you don't already have it. Then I also need you to go and start where we left off on the code in lesson number 8. I can give you a real quick recap of how to get there. You need to go to www.toptechboy.com, and then I need you to search on 9-axis IMU lesson number 8. Okay, go to lesson number 8 and you can grab the code there, which is the code we're using as the starting point for this project. Now let me come over and kick this thing off, bring it back to life, and then let's just take a few minutes and remember where we left off in this earlier lesson, in lesson number 8. If you remember at this point, and let me kind of tell you what we're going to do. I'm going to show you how to implement a complementary filter. Okay, a complementary filter is a filter that will kind of take the best of both worlds. It will combine the data, the tilt data coming off the accelerometers, and combine that with the tilt data coming off of the gyros, and combine that in a clever way where we sort of get the advantages, or get the best of both worlds. We get the advantages of the accelerometer combined with the advantages of the gyro, and what our goal is to get something that is both quick to respond and sort of immune to vibrational noise. And so that's what our goal is today. But let's come in and look at this thing, and let's see if we can just remind ourselves of where we ended up in lesson number 8. Okay, I am looking at the data coming off the sensor. What do I have turned on right now? It looks like I have the raw tilt number, the raw theta number coming from the accelerometer, and I have the raw phi number coming off of the accelerometer. And so that's sort of like I'm looking at the pitch determined from the accelerometer and the roll determined from the accelerometer. And by the way, these are the unfiltered data. Remember, we did some work to try to filter out that vibrational noise, and we had some moderate success with that. But what we're looking at right now is the unfiltered data. And so let's kind of go back and review this. So what I'm going to do is, if you look, the pitch, which we're going to call pitch, this is the nose, and bringing the nose up would be pitch. So what we're going to look at is the raw pitch number coming off of the accelerometer. And so I am going to lift the nose up, and what you can see is that green curve is looking at tilt as calculated from the accelerometer, and that looks really good. And now I'm going to look at roll from the accelerometer. That looks really good. Okay, so the data coming from the accelerometer looks really good, but what is the problem? The problem is if I do not tilt but I introduce vibration, the system inappropriately interprets vibration as tilt. Okay, so how did we go about trying to compensate for that? Well, we created a pitch or theta filtered and a roll or phi filtered, and so this is still just accelerometer data, but you can see that if I introduce a pitch, let me see if I can back this off a little bit so you can see this a little bit better. Okay, there you can see a little better. So now I'm going to incorporate a pitch, and you can see the unfiltered acceleration number responds very quickly, and the filtered responds slowly. But if I look and I introduce a vibration, that unfiltered is very sensitive to vibration, and the filtered is kind of immune to the vibration problem. So at this point, if I just try to use accelerometers and just do a low-pass filter, or this would be, yeah, a low-pass filter, what the problem is, I get something very stable, but it is somewhat sluggish. So if I introduce a tilt, it takes several seconds for the data to reach its actual value. So what is our goal? Our goal is to develop something that is both snappy and quick and stable. Well, what we introduced last week is we introduced the gyroscopes, and what we saw with the gyroscopes is that if we calculate the tilt based on the gyroscope, it is not susceptible to vibration. But what the problem is with the gyroscope data is it's susceptible to long-term drift. And so let me kind of show you that I left this thing running overnight, and I just kept taking data with the gyroscope. And so you see that we're sitting here nice and flat, but let's go in and see what our gyro data is reading. And so we're looking at that theta G, that is the pitch from the gyro, and we are looking at phi G, the roll from the gyro. And you can see you don't even see them on this scale, so I'm going to come in, I'm going to turn on auto scale, and what can you see that's happening? Overnight, the gyros drifted to where they think that they have a drift in the roll, the phi, of about 450 degrees, and in the pitch it's reading about 90 degrees. And so this thing has turned all the way like upside down and spun all the way around overnight because of this long-term drift problem. Now, if we look at the data, and again, you're looking at that top blue curve and you're looking at the bottom kind of brown curve, if I introduce a tilt, okay, look at the brown, and that is the pitch. You see it's still giving me short-term data that is really good, or if I look at roll, okay, up in the blue, that's looking good, but that change is on top of a really lousy signal. Okay, so what does this mean? Let's go in and let's kind of start breaking this apart. Okay, let's start breaking this apart and think about what we have. So I'm going to try to go to a better overhead view here. Let's see, does that do it? That is not the one I want. This is the one I want. Okay, so we're going to kind of come in here and try to review what we have done. Right now, we are getting a pitch theta from the accelerometer. Okay, we're getting a pitch from the accelerometer, and we're getting a roll from the accelerometer. What is good about this? This is very good in the long term. In the long term, if the accelerometer says that it's at 45 degrees, that is a very stable long-term measurement. But we can't trust it in the short term because of vibration. So for these two numbers, what can we say? We trust the long-term. We trust the long-term data coming off of them, but we don't trust the short-term data. We want to filter out the short-term data. So what does that mean? We want to take out the high-frequency stuff and we want to leave the low-frequency stuff. So leaving the low frequency, that means we want a low-pass filter. Okay, we want to filter out the high frequency stuff. Now, what did we also do? We also came up with a phi from the gyro, a theta from the gyro, pitch, and a phi roll from the gyro. And do we remember how we did that? Well, we said that this was the old value, the old angle, plus the omega times the change in time. And if you need this explained, you need to go back and watch lesson number 8. And then this phi sub g was equal to the old phi sub g plus the omega times dt. And then this pitch is rotating about the y-axis, so we use the y gyro data. And the roll is rolling about the x-axis, so we use the x gyro data. So the new pitch is the old pitch plus the rotational velocity along that axis times the change in time. And with this, we can get very, very good short-term data. So what do we do here? We trust the short-term data. We trust short-term. And let's go in and let's just kind of review that, right? Let's look at this. Let's look at this again by going back to where we were. Let's see. This might be a view that will show it. No, that is not. Okay, this will kind of show what we want. So if you watch, look at that top blue curve. That top blue curve is the roll that we get from the gyro. And you see, it says that it's at 450 degrees, and that's after running all night. Do we trust that? No. But if I roll it 45 degrees, do I get a good short-term measurement? Yeah. Okay. Do you see how I can trust that gyro in the short term, but I can't trust it in the long term? Okay. The accelerometer, I can trust in the long term. Look, it ran all night and it's giving me a perfect answer. But the accelerometer, I can't trust in the short term. Does that make sense? So we need to be clever about the way that we have this. We're going to keep what we've done so far. We have a pitch determined from the accelerometers, and we have a roll determined from the accelerometers. We have a pitch determined from the gyro, and we have a roll determined from the gyro. We're going to keep those four numbers, but now we're going to combine them in a way that will allow us to take advantage of the best of both worlds. And so how would we go about doing that? Well, let's start with the gyro. Okay, we said that the pitch from the gyro is going to, let's stop calling it pitch from the gyro. Let's just call this the overall system pitch. How would I get the overall system pitch using only the gyro? I would say the system pitch is equal to the system pitch plus the omega, and pitch is what? Pitch is like this, and that is rotating about the y-axis. So this would be omega y from the gyro times the change in time. Okay, now this is how we do it just with a gyro. Do I want to trust this in the short term? Yes, in the short term, I really want to trust that. So what am I going to do? I'm going to put a weight factor on here of 0.95. Now, what number you use here, you can tweak to get something, but this is, I'm building you mathematically a complementary filter. So if there is no omega, then you just kind of stay at where you were before. But if this omega kicks in, then you really trust it. You trust it and you put a 95% weight factor there. Well, what is the other 5%? The other 5% is the theta that comes from the accelerometer. And this is the unfiltered theta from the accelerometer. So let's see. Over time, if I'm not reading omega, omega is 0, and I'm getting the value just from the accelerometer, okay? And so don't think, oh, and I'm sorry, this should be times 0.05, okay? Because in a filter, this number and this number have to add to 1. And so what this is saying is that in the short term, quickly, if omega is changing, I want to give that a lot of weight. I put a 95% weight on that, okay? But if omega is not changing, this term goes to 0, and this are dominated by the acceleration data. So over time, you're always going to be moving towards what the accelerometer is saying, because I can trust that over time. But if along the way the gyro says things are changing, I am going to believe the gyro data. So in the short term, I believe the gyro data, and in the long term, I believe the accelerometer data. And so what this is kind of doing is it is putting a high pass filter on the gyro, and it is putting a low pass filter on the accelerometer. And with a little luck, this should give me something that moves quickly and is not susceptible to vibration. So let's do the same thing. The system phi is going to be equal to the old system phi plus the omega, and phi is what? It's roll, and roll is change around what axis? You're rotating around the x-axis, so I would use the rotational velocity of the gyro, the x gyro times dt times 0.95 plus the theta, or the roll, from the accelerometer times 0.05. Okay, now depending on your accelerometer and your gyro and your application, you can balance these things differently. You can tweak these. This is where the art comes in, is tweaking these things to get it to work where you want. But overall, you need these two to add to 1 and these two to add to 1. What have we just done? This is called a complementary filter. A complementary filter, and it's pretty easy to implement. So let's see if we can come up with a code view here. And so we are going to come back over to our code view, and let's see if we can get this set up. Doing the best I can with no help whatsoever here. So here is a nice code view, and let's kind of keep our eyes on these equations. Might actually work better if I went back over to this one. Yeah, there you can see. Okay, and then here we can keep our eyes on this. Okay, I believe this is going to work here. Okay, you can see the code. No, that's not right. You need to see the code view. Okay, so you can see the code. This will work. Okay, you can see the code as we're developing it. And again, this is where we left off. Darn it. All right, I'll just point this one here like this. And I want to see those equations as we are coding. And so we will do the best we can to see the equations as we are coding. There we go. Okay. Sorry, this would be easier if I had someone to help, but I don't. Okay, again, you need to call up that code that we ended up with in lesson number 8, and that's where we're starting. So let's see, we're going to need some new variables. Remember, this theta g was the theta from the gyro, the phi g was the phi or the tilt from the gyro. Well, now we're just going to need just a float, and this is going to just be our theta. This is our overall system theta, which is going to come from our filter, and then we need a float phi. So no more subscripts. We have a pitch and we have a roll, and that's what we are going to calculate. Okay, we come down here, and we are doing lots and lots and lots of calculations, so we need to come down to the point that we have actually calculated. So theta g is theta g plus the, okay, we don't want that. We want to just go where we've done the accelerometer. Okay, so where is the, this is the accelerometer data. Theta m is the pitch from the accelerometer, and phi m is the roll from the accelerometer. Then this phi nu and theta nu, those are the filtered values. So we're not going to be using those values. Over here, we're just using the raw number, the raw pitch from the accelerometer and the raw roll from the accelerometer, which are phi m and theta m. Okay. Now we still need to keep track of this dt, right? Do you see here how we still need to keep track of this dt and this dt? And so we're going to do the calculation after we have calculated the raw pitch from the accelerometer, the raw roll from the accelerometer, and we have a good number for dt. So if you look right here in the code, we have that accelerometer theta, we have the accelerometer phi, and we have a good dt. So now I am just going to calculate theta. And theta is equal to theta, the old theta, plus what? We have the gyro dot y, right? That's the measurement of rotational velocity about the y-axis times dt. Okay, we multiply that by 0.95, all right, and then I add just the theta from the accelerometer, which is theta m times 0.05, okay, semicolon. So that line of code should have just implemented this, and we have the advantages. We've already kind of built the components in the earlier lessons. Now we're just doing a calculation based on numbers that we already have. Now we also need to do the same thing on phi. So our system phi is equal to our old system phi plus gyro about the x-axis times dt times 0.95 plus phi from the accelerometer, which is phi m. I don't remember, what was I thinking when I was saying phi m? I don't know, maybe that's like measured, theta measured and phi measured, and it's measured from the accelerometer. Okay, so phi m, again, times 0.05. That's our filter value. All right, I believe that's good. Now the one thing, you remember how on the gyro, the sensor was kind of backwards from what we had called positive x and positive y. So we want to make sure that we compensate for that. Remember when we were looking at the gyro rotation about the x-axis, that the sign was different than how we had kind of defined things. So I better put a minus in here on this, okay? Because a minus of a minus, it'll make the signs all match up, if I'm not mistaken. And hopefully this is kind of like I'm thinking about it right. Okay. Now we are going to need to download this, and this is going to be a big one. Okay, so I need you to take a big swig of coffee, and I'm going to need you to hold your breath as we try to download this. Oh, download. Oh, denied. I know what's wrong. We forgot to turn that serial plotter off, right? You remember there can only be one thing. There can only be one thing touching the serial port at a time. So I need to turn that off by clicking on open. I believe that took care of that. Now let's come back. This time, the real problem was everyone did not hold their breath. So this time I need everyone to hold their breath. Download. Yes, please. Download. Oh, you're not even seeing all the excitement. Sorry. Let me come back over here. And boom, it did download. Okay, it did download. So now it downloaded, but we don't know if we're getting good data or not. So now we want to go back to the view where you can see the serial monitor. And then we do need to turn this back on. Okay. Let's see. There it goes. All right, now also, do you see now that the gyro has restarted? We restarted it, that the gyro is back down to at least a more reasonable value. And so once you kind of restarted it, the gyro just kicked in again. But still, we haven't changed anything. And what we have to see is that we've added 2 more channels. So we need to go to data format. And now we Oh, but wait a minute. What did I forget? What did I forget? You know what I forgot to do? I forgot to print it. I was calculating it, but I didn't print it. So let's see if I can just come up here. And I think you guys, for a simple thing like this, can see this okay. Let me make one quick, I think that'll work. Let me make, I'm a perfectionist. Let me make one quick change here. Okay. Okay, I didn't like that little black line. All right, so let's go back to our code view. First of all, I'm going to remember to turn this off this time. I turn the serial port off. And now I am going to come back to my code view. And what did I forget to print? I forgot to print this theta and this phi that I just calculated. So I come down here. The last thing that I'd plotted was the roll from the gyro, and I used a print ln there, so I don't want that because it's not the last one anymore. So now I got to put in my delimiter serial.print, and I'm going to put in my comma, and then serial.print. I think we are usually going pitch first, so I will print theta, just the system theta, which is the complementary filtered one. I will indeed need a new delimiter, comma, okay, serial dot print, and now I just want to print the phi. Okay, so, and what do I do on the last one? The last one I always need need to do the print ln, so then I'm kind of sending a packet of data that the serial plotter will know how to deal with. So I do believe that I want to come back like this, and I think you should be able to now see this again. Oh wow, these are some great views that I am getting here, aren't they? All right, so now I'm going to need to download, so I'll come back like this, and I will edit this. Give me just a second. I'm sorry that these shots are not always the first time like what we want. Okay, now we are going to download. So I come over here, hold your breath. Oh, please, 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 download, download, download. Oh, boom. Okay, we got it. We got it downloaded. That is a lot of high drama when we are trying to get that downloaded. So now let me come back to our earlier view. And I do believe at this point that we should be able to bring the serial monitor or the serial plotter back to life. And so we're going to turn it on. And it does indeed look like, is it going to come to life? Yeah, there it goes. It's come to life. And now we got to remember, here we go to data format down here. And we got to remember, we just added 2 more channels of data. So instead of 13, we are going to have 14 and 15 channels of data. And now on plot, we need to do our good bookkeeping, and we need to come in. And this was the, we'll call this the system, or this is the complementary filtered theta. And then this was, if I can get my mouse over here, the complementary filtered phi. Okay. And so now let's see, oh man, do you see all that data that we're getting? Let's simplify that a little bit. Okay, let's simplify that a little bit. And let's just look at the new things that we've added there. And so I'm going to turn all the other channels off, and I'm going to keep the final answer, the complementary filtered theta, which is pitch, and the complementary filtered roll, which is phi. And then I want to give you a nice view here where you can see what we're doing. I believe that is pretty good. Now, if you look, you've got to look at the scale. This thing is set to auto scale, and I don't want it to auto scale. I want to look between 60 and -60, so I'm going to untick auto scale, and then these things should really come down to, yeah, like 0. Okay, so this is the final answer. When I roll, are you going to see a roll? That is the question. When I roll, are you going to see a roll? And the roll is phi, and that is the kind of olive green. Okay, so I'm going to roll. Boom! Look at that. Did you see that? Boom. Okay. So now I'm going to roll. I'm going to come back down. I'm going to roll in the negative direction. Do you see how quick that is? Okay, roll. Okay, now what I'm going to do is I'm going to pitch. That looks good. I'm going to pitch, and that looks good. Okay, so do you see those quick changes? Those quick changes are coming from the gyro. Okay, the quick changes are coming from the gyro. But over time, when the gyro isn't seeing anything, you are going back towards that acceleration data. Okay, now the big question is, so would you agree that this is very snappy and is responding quickly? Okay, would you agree with that? Now look, if let me let it stabilize back to 0. Now I want to show you how that low pass filter that we have on the accelerometer is working. If I tilt, it responds very quickly, right? It takes that gyro data. And then I tilt back and look, it overshoots a little bit. It goes too far down. I got a little drift from that gyro. But then look, over time, that accelerometer is canceling out, and you kind of always come back to where you want to be. Okay, pitch, comes back a little overshoot. Pitch negative, looks good. Roll, looks good. Roll, looks good. Okay, do you see what I'm saying? That there was an error, but now that error is compensating out. Okay, I might look at this, and let's see if I'm susceptible to vibration. Boom, almost no susceptibility to vibration. Boom, almost no susceptibility to vibration. So let's compare that to our unfiltered. We're going to compare that to our unfiltered acceleration. Okay. And I believe that we did here and here. Okay, so this is the raw data coming from the accelerometers for pitch and roll. Let's look at it. Okay, so this one is going to be, the dark green is straight off the accelerometer. Okay, so straight off the accelerometer, do you see how the straight off the accelerometer is matching very well with our compensated? Okay, they're tracking very well, which is good. But now let's introduce a vibration, and what you can see is the accelerometer has huge vibration, but the compensated one doesn't. Now let's look at roll, same thing. Oh, look at that, the roll looks very good, and what makes me happy is the roll from the accelerometer, you know, we know is accurate, and our complementary filter is hitting that very well. Okay, what you can see is when you came back down with the filter data, you overshot it a little bit because you're really trusting that gyro so much. But what happens? That error goes away. So you see we're kind of filtering out the error. So we've gotten rid of this problem, and we've gotten rid of the long-term drift problem, and we've got something that is both snappy, okay, quick to respond, and accurate over the long term. Okay, this is just really, really exciting to me because I can't tell you how hard this is to do. Okay, now a couple of things that would really be the next things for us to do, and so this is going to be your homework assignment. So I'm going to deliberately give it a very, very fast, I'm going to give it a very, very fast roll, and then that's going to introduce an overshoot or an error in the filtered value. Okay, do you see how I ended up way up there, but then do you see how very quickly that error compensates out because of the action of the accelerometer? I hope this makes sense. We're taking the advantages, the long-term stability advantage of the accelerometer, and we're combining that with the short-term sensitivity advantage of the gyro, and then we're getting something that is both quick and accurate. All right, guys, I've always got to give you this disclaimer every lesson. This is just a project to impress your girlfriend, right? To say, oh, look how cool this guy is. He can do complementary filters on 6-axis data coming from a B&O 055. The ladies will love you for this, okay? But it is not to go in and build a control system on a Boeing 737. Things get much, much more sophisticated. This is for the simple home hobby thing of demonstrations. Also, even like an unmanned aerial drone, you don't want to use this on an unmanned aerial drone because any error, you know, that thing could fly into somebody's face. So this is for demonstration purposes only. It's allowing you to begin to understand non-axis inertial measurement systems. Okay, guys, has this made sense? All right, I'm sorry. Let me get back to your homework assignment. Your homework assignment for next week is to, let me come back to my code view. And then we are going to come over here and we are going to look at this complementary filter that we put in, which was right here. No, it wasn't. I lied. This was the complementary filter. All right. And do you see how we put a 0.95? We put a 0.95 factor on the gyro, and we put a 0.05 factor on the accelerometer. And do you see when I changed real quickly, this was kind of overshooting because of trusting the gyro too much and undershooting, trusting the gyro too much. What you can do is you can play around. Maybe you should tweak this down a little bit, and maybe you should tweak this up a little bit. There's another thing that you could think about doing. What if instead of using the raw phi from the accelerometer, what if you use the filtered phi from the accelerometer, okay, and then maybe trusted it a little bit more, and then maybe trusted the gyro a little bit less. So you've got two parameters to play with. One is, do you use filtered or unfiltered acceleration? And then secondly, what is the factor that you want to put on this? What is the factor that you want to put on this weight factor on the gyro versus the accelerometer? And you can play around with those and see what you think gets the best combination of quickness and stability. The kind of limitation that I see we have right now is where if we're making quick moves, we're tending to overshoot. The gyro is kind of overshooting a little bit, and then it takes a little bit of time for the accelerometer to get those things normalized out. So I think this is just pretty cool. I don't know, it's just to me so neat to then be in a situation where, you know, you actually have a problem and you get rid of that problem using math and using engineering. This is just really lovely. This is just really lovely how this thing is working. So you've got that homework assignment, guys. The other thing that you can see is that really, if you wanted to tweak this further, the more accurate you are is the smaller that the DT is. So the quicker that you're making the measurements and the more accurately that you're measuring DT, the better off you're going to be. And so you might start thinking about, like, if you're a more advanced user, using interrupts and getting that DT as small as possible. And then also a way we could speed things up is, right now I'm printing all the data and those print statements are slow, so I'm slowing my time through the loop up because I'm printing a bunch of stuff for development. Now what I would do is I would take out all the print statements except the ones that I really need, and then I would get the whole thing working a lot quicker. All right, is anybody out there listening? We're on lesson number 9. Have you all guys gone back to like your silly cat videos or things like that, or is there anybody out there that is actually sticking with this series? Because I need your feedback, because I don't want to keep doing these things if there's nobody playing along at home. Did anybody make it to the end of the video? Think about giving us a thumbs up. Leave a comment down below. Let me know how this is working for you. Let me know if you're keeping up. Let me know if it makes sense. Let me know if you have other ideas. Think about sharing this with other people. Would love to get more people playing along at home. Okay, this is Paul McWhorter from TopTechBoy.com. I will talk to you guys later.